Hello everyone. In this video we're going to talk about one-way independent measures, ANOVAs. We're going to briefly talk about when you use an independent measures one-way ANOVA, the logic of ANOVAs, and the 4 pillars of scientific reasoning, including hypothesis testing with continuous p-values, assessing practical importance with effect sizes, looking at population estimation with confidence intervals, and then also considering the statistics in a research and scientific context. You're going to choose to use a one-way independent measures ANOVA when you have one independent variable that creates 3 or more groups. So when you do this, you're going to have multiple groups and your dependent measure has to be measured on an interval ratio scale. That way you can compute averages across those multiple groups. Now, in this case, we're going to focus on 3 or more groups for using an analysis of variance. You can also technically use an ANOVA, an analysis of variance, when you have just 2 groups. It's just that most people usually use t-test when comparing 2 groups. So we're focusing here on the 3 groups. So there are 2 different kinds of one-way ANOVAs. There's a between subjects one-way ANOVA and a within subjects one-way ANOVA. Between subjects is where you have different people in the 3 groups. Within subjects is when you have the same people in the multiple groups. So we're focusing in this video only on the between subjects or independent measures designs where you have different people in the different groups in the study. ANOVA is short for analysis of variance, which, as you could guess from that name, it means we're going to be analyzing the variance or the variability in a given study. So for any study, you can have variability or differences in your scores from 3 different sources. You may have variability due to measurement error. Right? You might have variability due to individual differences between people. And you might also have treatment effects, and that's the effect of the independent variable on the dependent variable. Now, all studies have the possibility of having differences in the scores or variability due to measurement error or individual differences, right? There's always the possibility that there's been some problem with the measurement, even when you're recording very simple physical measurements like height, right? Sometimes those numbers are going to be a little bit different. Likewise, we're always going to have individual differences because we have multiple people in our studies and they're all a little bit different in a variety of ways. Now, what you as a researcher are hoping to determine when you manipulate an independent variable is that you also have variability or differences in your scores due to that treatment, and that's called treatment effect variability. So when you're computing an ANOVA, you get an overall F ratio. You're going to compute this F ratio, which is computed as the variability between treatment conditions divided by the variability within treatment conditions. So the numerator here is variability between treatment conditions, and you can have differences or variability between treatment conditions for 3 different reasons. One reason may be that you actually have a treatment effect, right? You treated your different groups differently in your study, and so you'd expect them to have different levels of scores. You also are going to have variability due to individual differences because you have different people between your 3 treatment conditions with that one-way independent measures ANOVA. And then you also always have the potential for measurement error. In the denominator, you're going to look at the variability within treatment conditions. So within treatment conditions, there's no possibility of a treatment effect because everybody in that condition received the same treatment. So but within conditions, the only sources of variability you have are individual differences in measurement error. Right? So you can see if you look at this F ratio that your numerator and denominator are the same with the exception of treatment effects. So if you have a treatment effect, you would expect the numerator to be larger than the denominator. So let's look at this idea of variability with an example. So let's say that I'm interested in the effects of exercise on people's mood. And to study this, I obtain a sample of people. So this group of people here represents my sample. Now you'll notice that all of these people are different sizes, they're different colors, they bring individual differences to the study, right? They're different people, they have individual differences, and those differences are going to lead to different scores. They're going to lead to differences in variability in our data. Now we're going to measure people's mood in this study. So let's say we do something simple. I have this 5-point scale where people rate on these faces their overall mood, where 1 is the worst mood and 5 is the best mood. Right? So this is one way to measure mood. It's very quick, it's very easy, but as with all measures of mood or anything, there's also the potential for measurement error. Right? So people are going to have different scores on this measure of mood that we're going to use, in part because of error in measurement in terms of using this particular scale for measuring their mood. Right? So now we already have two sources of variability or differences in our data. We have measurement error and we also have individual differences. So let's imagine that I randomly assign people into 3 different conditions. I have a running group, a biking group, and a control group. Right? So I have different people in each of these groups, and so they bring individual differences to those conditions. So if you look at the formula for the F down at the bottom, it's more of a conceptual formula for the F down at the bottom of the screen, you can see that we're looking at the numerator being treatment effects, individual differences, and measurement error, and we're going to divide it by individual differences and measurement error. Right? My numerator there is looking at between treatment variability. The denominator is looking at within treatment variability. And so I'm going to expect a bigger numerator than a denominator if my treatment works, because only the numerator takes into account treatment effects. All right, so let's try pooling all of this together into one example. And the example we're going to work with is, does temptation bundling increase the frequency of people's workouts? So most of us know that working out is good for our physical and mental health, but many of us struggle to get enough exercise to realize these benefits. Research has revealed that people are more likely to exercise when they use temptation bundling. And basically, this means that we're more likely to exercise if we pair something we find pleasurable, like watching movies or listening to podcasts, with something we need to do, like exercise. So previous research has already revealed that this technique of temptation bundling can be effective. And so what we're doing in this study is trying to replicate previous research at a local YMCA. In this study, we're going to have 3 different groups. One group is going to receive an audiobook. The second group is going to receive an audiobook, but they're also going to receive instructions on temptation bundling. So they'll be given things like this cartoon off here on the right, where it shows them an idea about exercising, where you want to pair up exercising with something you really like to do, like watching TV shows or audiobooks or music. And then only do the things that you want to do when you're doing the thing you need to do, which is exercising. Right? So that's our second group. Our third group is a control group that receives no audiobook at all. Right? The dependent variable we're looking at is the number of visits each person makes to the YMCA in a given month. In this study, we're going to start with a population of members of the YMCA, and then we're going to select a subsample of those YMCA members to participate in our study. After we've selected our sample of people to be in the study, we then randomly assign that sample into 3 different groups of people, representing the 3 treatment conditions we're going to have. The 3 groups we're going to have are the audiobook alone group, the audiobook group where they're encouraged to temptation bundle, so they're only supposed to listen to that audiobook while they're at the gym, or a control group that doesn't receive any instructions, nor do they receive an audiobook. Then at the end of a month, we're going to measure our dependent variable. So for each person, we're going to measure the number of visits they make to the YMCA. All right, so now that we've looked at the general layout of the study, let's consider the 4 pillars of scientific reasoning. We're going to look at hypothesis testing with continuous p-values, assessing practical importance with effect sizes, determining population estimation with confidence intervals, and then also putting this into a scientific context by considering the research methodology and the scientific literature. All right, so our first pillar here is hypothesis testing with continuous p-values. In order to conduct our hypothesis test, we're going to follow through with 5 steps. The first is choosing the correct statistic. The second is examining the statistical assumptions. The third is identifying the null hypothesis. Fourth is graphing the sample data. And then finally, we're going to compute the test statistics, determine the p-values. Okay, first, before we start doing any statistic, we have to make sure we're actually using the correct statistic. In this case, we use an independent measures one-way ANOVA when we have one independent variable with two or more groups, and our dependent variable is measured on an interval ratio scale. In this case, we have three groups, and that's the audiobook, the temptation bundling group, and the control group. And we're measuring their number of visits to the gym, which is measured on an interval ratio scale. Next, we need to consider the statistical assumptions for this test, because all statistics have particular assumptions, and your results can be really misleading if your data violate these assumptions. So one-way ANOVAs have four assumptions, and that's independence, appropriate measurement, normality of distributions, and the homogeneity of variance assumption. The independence assumption means that each participant's score within a condition is independent of all the other participant scores within that same condition. Okay, so everybody within the audio group book score needs to be independent of all other people's scores within that same condition. So in this case, you need to be careful to recruit people who aren't, say, all in the same family, who may be coming together, right, and interacting, and they may influence each other in terms of how they are likely to come to the gym. All right, our second assumption is appropriate measurement, and that means that our dependent measure, in this case, it's going to be number of visits to the gym, needs to be measured on an interval ratio scale. And number of visits to the gym is measured on an interval ratio scale. Finally, our normality of distributions assumption, we have to make sure that our distribution of sample means is normally distributed. Right? So this is about the distribution of sample means, not the scores. And as long as our sample size within groups is at least 30 or higher, we can be confident that this assumption is met. Note that this is 30 per group, not 30 in the entire study. In this case, we have more than 30 per group, and so we can be confident moving forward with this. Our last assumption is the homogeneity of variance assumption. And this assumes that the three sample variances are estimating the same population variance. So to determine if this assumption is met, what we're looking at is the standard deviation for each group. And so you can see in the table below under group descriptives, the standard deviations for our groups are 7.36, 6.99, and 7.08. So as long as one of them is not like 3 times as large as the other, this assumption is probably met. Right? But it's also a good idea to look at the homogeneity of variance test. This is the Levene's test, and it will compare these 3 variances for you to tell you if it seems like they're estimating the same parameter. In this case, our P for the Levene's test is 0.89, which tells us that the data are consistent with the null, and the assumption is probably met. So based on this information here, we can be confident that our data do not violate this assumption. Our next step is to identify the null hypothesis. So for the one-way independent measures ANOVA, our null hypothesis is always that all the means in the study are equivalent. So any difference we're observing between groups is due to sampling error. In this case, we have 3 different means, and so our null hypothesis is that the 3 population means are all equivalent to each other. Next, we have a graph of the sample data. So I've already generated the graph here, and I'm not going to show in this video how to create graphs or how to analyze the data in software. There are other videos for that. Right now, I'm just walking through the logic of understanding the ANOVA. So in this case, we have 3 different groups. We have a temptation bundling, an audio group book, and a control group. And you can see that our temptation bundling group appears to have visited the gym more often than the audiobook group, and the audio group seems to have visited more often than the control group. So you can see that both in the graph and in the table of descriptive statistics. But what we need to do with our overall ANOVA now is determine, well, are these differences real, or are they likely to be due to sampling error? When you're doing an ANOVA, your first step is to compute an overall or an omnibus F. And this F ratio is the ratio of between treatment variability to within treatment variability. I did these analyses in Jamovi. Your output might look a little bit different in terms of how it's labeled, but it should be really similar. Now, between treatment variability in this software is labeled as group, and then the within treatment or error variability is labeled as residuals. Okay. The F is the ratio of the variability between to variability within, and that F value generates a p-value. Okay. We're not going to focus on computing the statistics right now by hand, but if you're interested, the formulas are listed there below so you can see the interrelationships between the numbers in the table. So in this case, our F is 9.62 with a P of 0.0002. When you're reporting an ANOVA, you report the F and then in parentheses the degrees of freedom between treatments followed by the degrees of freedom within treatments. And then you give the F that was computed, the p-value, and MSE is mean square error, which is the variability within treatments, or in this case it's called mean square residuals. So mean square error, mean square within, and mean square residuals all mean the same thing. So our p-value here is quite low, right? We have a p of 0.00015. So this is a low p-value, and it's telling us that the probability that I would obtain an F as high or higher than the one that I obtained in this study is low. It's 0.0015 if in fact the null hypothesis is true. Okay. So this provides some strong evidence against the null hypothesis, right? Our null was that all three means were equivalent. And so this is telling us that, well, that's probably not true. There seems to be at least one difference in there between the means, or maybe more than one difference, that's larger than what would be expected due to sampling error. And so we need to do some further tests in order to investigate this in a bit more detail. Okay. One quick note before we do that, F's are the ratios of two variabilities to each other. As such, the F's are always going to be positive. So your p-value is always the probability of getting an F as high or higher or greater than the one that you computed. There are no negative F values. All right, so our overall ANOVA shows us that all three means are not equivalent, that at least one of the differences between the means is different from each other, right? It's unlikely to be due to sampling error. And so what we do next is post hoc tests. There are actually a lot of post hoc tests to choose from. In this case, I'm focusing on the Fischer Lsd post hoc test, which is the Fischer Least Significant Differences test. And the formula is there at the bottom of the page. But what you really need to know about this test is that it doesn't take any corrections or make any corrections to the p-value. So there are a lot of post hoc tests, and many of them change the p-value for a variety of reasons, mostly because people are concerned that if they're doing a whole bunch of post hoc tests, that every test increases the chances that you're going to accidentally find a difference that you think is real that really is not, that's just due to sampling error. That's really more of a problem if you're doing a lot of comparisons. And in this design, we only have 3 groups, so we're a little bit less worried if we're only doing 3 comparisons. But it's also more of a problem if you're using a hard and fast rule about cutoff levels for p-values. In this case, we're not. We're using p-values as a tool to help us think about our post hoc tests and think about our pairwise comparisons in our data, and we're not going to just use hard and fast rules. So in this case, this Fischer Lsd test is utterly appropriate. Okay. So we have 3 groups we're comparing, and we have the means listed there in the first table. The bundling group had a mean number of visits of 18.85. The audiobook group had a mean number of visits of 14.06, and the control group had a mean number of visits of 11.21. Now the next table shows us all of the pairwise comparisons. The first comparison is between the bundling and the audiobook group, and the mean difference between those 2 groups is 4.79. The p-value for that comparison is 0.008, which tells us that the bundling group and audiobook group are different than each other by more than what would be expected due to sampling error, or that difference is probably not due to sampling error. And I can see that the bundling group went to the gym more than the audiobook group by 4.79 days. The next row is comparing the bundling group to the control group. Here we have a mean difference of 7.64 with a p of 0.00004, a very low p-value, telling us that that difference is unlikely to be due to sampling error. And that difference is in favor of bundling. The temptation bundling group went to the gym more by 7.34 days or 7.64 days. Now finally, we have the audiobook only compared to the control group. There the mean difference is 6.85 with a p of 0.10867, right? And so here our p-value is higher. Right? That's pretty weak evidence against the null. I'm not very confident there that that difference that I'm observing between the audiobook condition and the control condition is real. It's pretty likely that it's actually due to sampling error. I want to repeat this study to investigate that further. Okay. So we have here this overall finding from our post hocs that the bundling group exercised more, went to the gym more times than the audiobook only group or the control group. But the audiobook and control group, we're not sure if there's a real difference there. It seems likely the difference we're observing is just due to sampling error. All right, so our overall p-value from the omnibus F showed us that, yeah, it looked like there was an overall difference. All three groups were not equivalent. And then we did post hoc tests and discovered that the temptation bundling group appeared to exercise more than the control group and also more than the audiobook group. Whereas the audiobook group and the control group did not appear to be different from each other. Okay. Now we need to look at the size of the effect, and we're going to look at effect sizes for this second pillar here. So we're going to start with the effect sizes for the overall ANOVA. Now, when you do the ANOVA in your output or in your statistical program, the output will show you and give you the option of selecting an effect size. And there are typically three options. There's eta squared, partial eta squared, and omega squared. Okay. So eta squared and partial eta squared are going to give you the same values for the one-way ANOVA, so I'm not going to focus on that difference right now. I want to focus just on the overall difference between eta squared and omega squared. Okay. The formulas are off to the right on the screen there, but what you'll see is that some programs only compute partial eta squared or eta squared, and so you'll see this reported in a lot of studies. Right? And it's interpreted as the percent of variability in the dependent variable that's explained by the independent variable. However, eta squared tends to overestimate the effect size in the population, so researchers often prefer to use omega squared rather than eta squared. And that's what I'm going to use here. It's a less biased estimate of the population parameter. So I'm going to use omega squared. Now, our guidelines for interpreting eta squared and omega squared are identical. Around 0.01 is small, around 0.06 is medium, and around 0.14 is large. So our omega squared for this study is 0.15, which is a large effect. So if I put this into our APA style summary statement, people put it right before the mean square error there. So we have a large effect. That tells us that overall, which group you're in has a big effect on the number of times you went to the gym. All right, so in addition to this overall ANOVA effect size, what we really want to do is describe the size of the effects when we're comparing each group to the other groups. So if we start by looking at this bundling group compared to the audiobook only group, we can see that the mean difference in raw score units is 4.79 days. That's a pretty big difference, right? 4.79 days in a month is quite a bit more visits to the gym. Cohen's d for that comparison is 0.67. So that's also a medium to large-ish effect, right? It's a fairly large difference. When we compare the bundling to the control group, I have a much larger mean difference, 7.64, with an effect size d that's standardized as 1.07. Right? So that's a very large effect, right? And that makes sense descriptively if you're looking at the mean difference of 7.6 more days a month. That's a big difference. So the bundling group compared to the audio group had a medium to large difference. The bundling group compared to the control group had a very large difference. And then if we compare the audiobook only group to the control group, we have a mean difference of 2.84, which, almost 3 more days a month. And D there is small to medium with a D of 0.3986. So after describing the effect sizes, we're going to move on to estimating population parameters with confidence intervals. So we're focusing here on confidence intervals around each mean difference or around D. So depending on which program you're using, it may give you a confidence interval around the standardized effect size, D, or it might give you a confidence interval around the actual mean difference in raw score units. So I have actually two outputs here to show you both. When I do the analysis in Jamovi, I get a 95% confidence interval around D. When I do the analysis in JASP, I get a confidence interval around the raw scores. Either one's fine, right? They both give you a nice way to estimate how wide your confidence intervals are. You just need to be mindful of which one you have in your computer program that you're using. And they're all interpreted the same way. I can be 95% sure that the true mean difference in the population falls between the lower and upper bounds. Or if I'm looking at D, I'm 95% sure that the true mean difference in terms of standardized units, or D, in the population falls between those upper and lower bounds. So if we look at the Jamovi output where we're looking at Cohen's D with the 95% intervals, our first one, the confidence interval around a D of 0.67, is that the confidence interval lower bound is 0.17 with an upper bound of 1.17, right? That's a really big range, right? So it tells us I'm 95% sure that the true effect size in the population is between 0.17 and 1.17. That's because of two things. One is a smallish sample. You need a bigger sample if you want a more precise estimate there. But also there was a lot of variability in our data set in terms of how often people went to the gym. And the more variability you have in the data set, the bigger the sample sizes that you need in order to get a narrower confidence interval. Okay. You can also see our confidence intervals looking at the JASP output when they're looking at the mean difference, right? With a mean difference of 4.79, we have a lower bound of 0.60 and an upper bound of 8.998, right? So again, a wide confidence interval that would be helped a lot by having a bigger sample size. Okay, now that we've considered p-values, effect sizes, and confidence intervals, it's time to pull this all together and relate it back to the scientific context. When we're considering the scientific context, we want to think about the methodological rigor of the study, as well as how the study fits into the scientific literature. So when you're thinking about a study, I know in these cases we don't give you a ton to work with, but this is worth thinking about. And that was a study well done with proper controls. Does the sample represent the population well? Was your independent variable manipulated well? And was your dependent variable measured well? So in this case, you can consider, does your sample of people at the YMCA represent the population well? Okay. When you manipulated an independent variable, did everybody get the audiobook that you said they were going to get? Did they all actually watch the training about temptation bundling if they were in that group? When you measured the dependent variable, are you sure that you actually counted the number of times people went to the gym? And are you sure they actually worked out, or did they just go, use the hot tub and then leave? So you have to make sure that these things were done well in the study. Okay. You also need to consider how your study fits into the existing scientific literature. So we based this study on a previous study that had found that temptation bundling was effective at getting people into the gym more. They have more visits to the Y. So this is consistent with the current research, right? This shows us more evidence. The weight of the evidence is stronger now, suggesting that temptation bundling is an effective way to help people increase the number of workouts they do. Now finally, we're going to pull together all four pillars into one big, well-supported scientific conclusion about this study. I'm going to start with an APA-style summary of the results. So I start by saying the analysis we did. So we computed a one-way ANOVA with the treatment condition as the independent variable and the number of visits to the YMCA as the dependent variable. And then I provide my statistics. So I have my F, and then in parentheses are the degrees of freedom. Between degrees of freedom was 2, within degrees of freedom, or residual degrees of freedom, was 96. The F we computed was 9.62 with a P of 0.0002, and our effect size omega squared was 0.15 with a mean squared error of 51.06. Note that I'm reporting these numbers to the second decimal place, but for the p-value, I take it out a little bit further since the p-value was so low rather than rounding it off to 0. Now, next thing you do with ANOVAs is present all of your data in a table or two tables so that you don't have to refer to it in the text. It's way easier to do this in a table. You could do it in the text. We're just choosing to do it in tables right here. Now my first table is just descriptive statistics for each condition. I have the means and the standard deviation for the temptation bundling audiobook group and the control group conditions. In my second table, I have the results of the post-hoc test, where I have mean differences, confidence intervals around them, the p-value for that comparison, the standardized effect size D, and then also the confidence interval around D. Now you don't typically have to include confidence intervals around the mean difference and D. I'm providing both of them here because your output, your program may only do one of these or the other. Now next, I need to describe these results. So when I'm describing the results, I need to describe the post-hoc test. And what I'm saying here is that I did Fischer post-hoc test, and they revealed that the temptation bundling group visited the YMCA more often than the audiobook group and more than the control group. Also, these results these differences were unlikely to be due to sampling error. The audiobook group visited the YMCA more often than the control group, but the evidence against the null hypothesis is weak, and that difference may be due to sampling error. The post-hoc test results are in table 2. So this way, again, you don't have to present all those numbers in the text. You can focus on a verbal description for people. And then finally, in my conclusion, I need to talk about the scientific context in terms of the research methodology and the existing data. And these results are consistent with the existing data, suggesting that temptation bundling can increase exercise. And there were no obvious methodological flaws with the study, but the confidence intervals were wide, and so we should consider replicating this study with a larger sample size so we can get more precise estimates of the population parameters. If you'd like more information about this study, here's one reference you can look at, and they will also point you to other references in that article that would be interesting if you're interested in this topic. In this video, I walked through ANOVAs very broadly here, but didn't show you how to do the actual analyses in any programs. If you check out our website, you'll see videos there for how to run the ANOVAs in different programs as well. All right, I hope that helped. Good luck with your statistics.